Hello, everyone. Thank you for joining us. Welcome back if this is your third time joining us, and welcome if this is your first time. So my name is Judy Gichoya. I am a resident at Indiana School of Medicine, and I help coordinate this, the Journal Club. And so we're doing this now. No financial disclosures. I'm not even eligible to vote, so nothing that can affect my decisions here. So a few announcements. We're still deciding on the topic of our next journal club. I think we are leaning heavily to an FDA theme. This week we had good news when Viz AI was granted, sort of like a good sign that they're going to get FDA clearance for AI software in radiology. So we have two companies, Ateris and Viz AI, with products. And so we thought an FDA-themed approach would be a good discussion. And especially, we're waiting on the FDA to see if they're going to publish the documents and the groups, if they'll publish their papers, so that we have enough content and a good panel to discuss this. And so the other thing is, from our last journal club, we still continue to have some of the conversations on Twitter. For example, about the data labeling. And so some of these conversations are not available if you're not beyond the, beyond the discussion. And so what we've started to do is, all radiology residents have access to the ACR Engage forum where we can continue our discussion, and this is good. But this forum, just because of the ACR membership as of this moment, is limited to just the medics. And so one of the things that we've done pretty well, I think, is to have a hybrid of people who come together, medics and the scientists. And so we're doing this thing where we're calling the tribe.radai.club. So go there, join in, and where you can post some questions. And so today I want to actually highlight one of our participants, Akshif. He's a radiology resident from Columbia University, has, previously prior to medicine, computer science, and he has been working to develop tutorials for the residents who want to learn programming, but very focused on, people who work in radiology. And so if you come in here, you'll start to see some of this content. And I think this is pretty exciting for us, because maybe in 1 year, we'll have a good group of people who can do like the first AI class together. And so, as always, thanks again to the Advisory Council. These are amazing people who make the magic happen at the back there. And a special thanks to Catherine Haas, who's our ACR admin assistant. She does a lot of work to make this happen. And so I'm going to, the reason why we're all here today, we have a special guest, Dr. Timney. She is our first female speaker, so I'm pretty excited about this. And so we'll have the same forum, the same format where we have a 30-minute presentation and 30-minute discussion. And so to recap our last two journal clubs, we looked at radiologists as knowledge experts in a world of AI, and then looked at the AlexNet paper to see how to read and critique deep learning papers. Now, if you remember, all these papers kind of tell us that all this work has been done around cats, dogs, planes. And so, it's a little ridiculous if you think about it, that some of the first image models that are used for training medical data are based on cats and dogs. And so I felt it's good that if we see how a deep learning scientist approaches this, like an approach to machine learning and AI, in their work, because I think we can borrow a lot from just their work and just their thought process. And that may be really difficult to talk about in 1 hour or in one journal club, but give us some points that we can explore over the next month in blog posts. So join me, please, in welcoming Dr. Timney. If we probably had a more recent change to the article, would be looking at racial bias. She recently published on this, and but today she's going to talk about using deep learning and Google Street View to estimate the demographic makeup of neighborhoods across the US. So welcome, Timney. These are some of the questions I emailed her just to make sure that she answers some of them during this 1 hour presentation.
Yes. Thank you. Can you hear me?
Yes.
Okay. Let's share my screen. Are we seeing my screen now?
Let's see. I am not able to see your screen.
Okay, let's, maybe I can't do presenter view in this form. Let me see if I can just slideshow. What about now? Still you can't see my screen?
Nope.
Maybe if you try to share your screen again, I do that sharing my screen again, and then I can click OK again.
I'm able to see it as well.
Okay, Catherine.
Yes, I'm able to see it. If the attendees are also able to see, would you mind posting in the chat just really quick, just to make sure that we're all on the same page here? Okay.
Who, me or
yes,
other
okay. So it looks like the attendees are able to see. So
okay,
I think we're able to proceed.
Yep.
Okay, actually, let me just see if I can do presenter view so that I can make sure to keep my time. Is this still okay for you guys, or are you seeing a different view now? Maybe you can tell me in the chat. Like, is this view okay, or are you seeing a different, like the same view I guess I'm seeing?
Looks like people are still able to see your presenter view.
Okay, so that's fine then. I'm just gonna go back to the old one. Okay. All right, so, but this one is fine? Sorry. The one I have right now is okay?
Yes.
Okay. Okay, good. I'm just gonna start. So thank you, Judy, for inviting me. I am happy to talk to an audience like you guys. But it's going to be a little bit of a different probably talk than many of the deep learning talks base talks that you have talked about, because I'm not going to talk too much. I'm actually going to say very little about the models I use that we use for this project, because we really use off-the-shelf models for this project. And so the question is, why did it take my entire PhD to do this project? And the whole, we wrote 3 papers actually based on this project, and all of them most of them, the difficulty was centered around gathering data. So that's mostly what I'll be talking about today. So I'll start with the motivation for, I'll start first with the financial disclosure. So this research was mostly funded by the NSF, and then there was also a Stanford DARE fellowship given to me, and then the NVIDIA that donated GPUs for our project. So the whole motivation for this project is that the U.S. government tries to spends a lot of money trying to understand the demographic makeup of its constituents, right? They want to understand what the racial makeup is, or maybe like occupation, age, et cetera, of people who live there. In the meantime, there are people who try to figure out who the next president is going to be, or other kind of politicians, and who's going to win. And there's people trying to figure out what different neighborhoods' crime rates are and how to reduce crime rates. Basically, there are people who try to use survey-based data to understand various characteristics of cities and neighborhoods. And the one question we wanted to answer is if we could do this using images and using computer vision, because at the time when we started working on this project, there was no sort of data mining really using computer vision and images. Except for this one work. The earliest work I know that's very similar to ours is from MIT Media Lab, and from 2013. And so what they do is they looked at Google Street View images, and so they used crowdsourcing, and they would show people 2 different images of 2 different places, and they say which one of these places is of a place that's looks more unique or wealthier, or what's another one? More unique, wealthier, I forget the third one. Anyway, so they ask these questions to participants, and then they take the answers that these participants give them, and then they annotate these images with the answers that the participants give them. And so then they created a data set in that form where there is each Google Street View image has an associated rank of how unique or wealthy or safe it is. Subsequently, once this data set was created of at least 1 million images, various computer vision researchers tried to use different methodologies to try to predict these labels of safety, uniqueness, and wealth. One of these was from Berkeley, where they looked at different image patches, and they managed to associate with these different image patches with different characteristics. And so they found some really interesting things, like, for example, high ceilings are very highly correlated with expensive neighborhoods, or hedges or are very correlated with expensive neighborhoods, etc. And most recently, there was a very famous paper, I guess from the AI lab at Stanford, where they tried to predict poverty rates in 4 different African countries, so Nigeria, Tanzania, Uganda, and Malawi, using satellite imagery. And so the question is, what is missing in all of these works? So all of these works try to associate global image features with various characteristics. So what do I mean by global image features? I mean, it could be like it looks at the picture as a whole and tries to extract characteristics of the picture as a whole. So it could be color histograms, or it could be other characteristics of the picture as a whole. And so the question is, how can we do better? And so our insight is that a city's objects help us understand what's in the city, right? So for example, here you see lots of yellow cabs, you see a crowd, you see billboards, and you're like, yeah, this is New York, and actually this is Times Square, New York. So that was the insight. We're like, okay, what we're going to do is we're going to use a city's objects to help us learn about the constituents of the city. And because we're computer vision researchers, and our lab used to run something called the ImageNet Challenge. So here I'm showing you the top 5 error rates on the y-axis and the year. And so the ImageNet Challenge, every year, people submit algorithms to do specific things like object detection or object classification. So object classification is like you have an image and you just classify what type of object is in that image. And you can see that the error rates have been steadily decreasing over time. And after 2014, they even surpass human error rates. So then you might ask, okay, great, like we can use object recognition. Object recognition is doing well in computer vision. So what makes this hard? Oh, well, before you ask that, you can say, okay, what if you're going to use a city's object to understand demographics, what sources of data do you want to use? What sources of images do you want to use? So we use images. We use Google Street View images. And why is this? This is because basically every single, many American addresses have an associated Google Street View image, right? So chances are, if I live in a particular area, there is a Google Street View image associated with that particular area. So now that I have my source of images, then the question is, okay, what objects am I going to use? And the answer that we chose is cars. Because why cars? Well, cars are a very dynamic and very personalized kind of expression of people. So if I told you I drive a 2008 Toyota Prius, which I don't, but if I told you I did that, you probably would have all sorts of stereotypes in your head about where I'm from. Like maybe I live in San Francisco, maybe I'm a Democrat, maybe I'm an environmentalist. You already have these associations of cars and people. And so the question is, can we extract this association using computer vision and millions of images? So we decided to detect and classify the cars in 15 million Google Street View images from 200 of the most populated cities in the United States, and then use the characteristics of those classified, detected and classified cars to then predict the demographic makeup of people in these cities. So great, it seems like we have everything figured out, and the question could be, what is difficult about this project? What's difficult about this project is, and I think this might be something that's relevant to this community. Sorry, I had to drink some water. Is that our object recognition that we're working on is something called fine-grained image recognition. And so what is that? Fine-grained image recognition is something, is basically trying to distinguish between highly similar objects. So it's different from trying to distinguish between a bird and a dog, or a bird and a tree, or a bird and a house. It's trying to distinguish between different types of birds or different types of cars, right? And so what's difficult about fine-grained image recognition? Well, you know, anybody can distinguish between a bird and a car, but only highly trained experts can tell you that this is bird species A versus this is bird species B. And similarly, only highly trained experts can tell you this is car type A and this is car type B. And with cars, we have another problem where with bird species, the taxonomy kind of tells you two different names of a bird species means they look different, right? Whereas in a car, you can have two different names, but on the outside, they might look exactly the same. So 2006 Toyota Prius, 2007 Toyota Prius here that I'm showing you, besides the color, I mean, here, we don't really consider color as a difference. On the outside, these cars basically look the same. And when we're looking at Google Street View images, we can only like distinguish cars based on what they look like on the outside. So before we even start gathering data, annotated data for each type of car, we have to figure out which types of cars look the same. And so we have to group different kinds of cars. So what we did is we first came up with a list of all cars that we could find. And so the most comprehensive list we found was on Edmunds. And so we found all cars since 1990. And then we had to figure out which one of these cars were visually indistinguishable. So maybe a 2005 Toyota, a Camry and a 2008 Toyota Camry of a particular trim might look the same because the manufacturer might not have decided to change the body, like how it looks on the outside within these couple of years, right? So the first task was to do this grouping. And so here I'm showing you, so maybe like the cars in red, should be in the same class. The cars in blue should be in the same cars, because you can see here, they look different, right? The blue-ish or the purple and the red look different, because I'm really highly trained. This is all I've been doing in grad school. I can spot the differences now. And then the car in the middle in the green is different from all of these. So here we've grouped all of these 5 cars into 3 classes. So that was the first task to do. And we want to do these tasks in a way that are not expensive, because we have a limited budget, and we want someone who's not an expert to do it, because experts are expensive. So what did we do? We tried to whittle this task down into a very simple task, a yes/no task, and we used Amazon Mechanical Turk. So how did we do this? So we represented each car, each type of car I showed you, as a node in a graph, right? So here might be 2005 Honda Accord LX trim or whatever, and then here might be 2006 Honda Accord LX trim or something like this. And what we do is we show people 2 different kinds of cars. So these are 2 different nodes in the graph. And we say, are these 2 cars the same or different? And so we show them examples of these 2 different cars. We get these example images from Edmunds.com. If they say yes, they're the same, we add an edge between these 2 nodes. If they don't say yes, there's no edge. And so we continue to do this until we add edges when they say they're the same. And we finally use connected components to get our class. So connected components is a clustering method in graphs. So this was a paper that we had, an HCI paper. So in this project, you learned that you have to do a lot of interdisciplinary things, not just computer vision. So this ended up being an HCI paper. And then we also had to learn later on, I'll show you some things about geographic information systems and things like this. So now we haven't even started gathering data. So in order to train a car detector or a classifier, you need a lot of images of cars that are annotated with the types of cars that are contained in these images, right? And so right now we haven't even done that. All we've done is we know which classes of cars we have. So then the question is, how do we get lots of images of cars annotated with the types of cars they contain? And the insight here is that I'm not an expert in everybody else's car, but I'm an expert in my car. And so when I'm trying to sell you my car, I will give you a lot of information along with the image of the car that I'm trying to sell. So what we did was we leveraged e-commerce sites. So we went to cars.com and Craigslist.com, and we basically queried these e-commerce sites, and we did some sort of a little bit of natural language processing afterwards to clean it up. But we ended up basically getting a lot of images annotated with the types of cars they contain. And this was almost for free because all we did was just go to these websites and scrape them. We had some sort of cleanup. We did some sort of cleanup tasks that we paid people for in Amazon Mechanical Turk. But besides that, it was relatively cheap to do this. Now we have a problem. The problem is that the types of cars we have in e-commerce sites look like this. They're like centered, they're large, you know, they're high resolution. There's no other object occluding them or in front of them. The types of cars we're trying to detect in Google Street View look like this. They are small, often blurry. There's one car in front of the other. Often the terrain looks different. So if we train a model, a car classification model, on something that looks like this, and try to detect cars on Google Street View images, it just doesn't work. I mean, I tried it, and you get like 4% accuracy. And then, you know, subsequently I started getting interested in something called domain adaptation, which is trying to figure out how to create models that work well even when your test distribution is different from your training distribution. Anyway, so we didn't do too much of that. We did something naive. But in this case, we had no choice. We had to take a subset of our Google Street View images and annotate them, excuse me, with the types of cars they contain. And now this is a very difficult task because now I'm showing you, I mean, we created a UI, a user interface to help people out, but I'm showing you a car like this, an image like this, and then you're supposed to tell me what kind of car this is. It's a very difficult task, but apparently there are people who are very good at this. So we guide them through this. So we ended up finally, after annotating a subset of our Google Street View images, we ended up gathering a huge data set of cars. So we have about, let's see, 500,000 images. Actually, we even have like 1 million images if you count some other bounding boxes we have. And we split them into training, validation, and test sets. So this took us about a year to get to this stage and about $35,000. And most of that $35,000 went into annotating the Google Street View images. So you can imagine we have about 500,000, let's see, 300,000, no, let's look at the bounding boxes. We have about 300,000 annotated, no, 300,000-ish product category labels that we spent about $5,000 maybe collecting these labels, and about 34,000 category labels for Google Street View images, which is the type of car, exact car that it contains. And that costs us about $30,000. So it's very expensive and time consuming to label data like this. All right, so now the question is, we have a data set. We now have to detect and classify cars in 50 million images in 200 cities. How do we do this efficiently? In 2014, the state of the art to do this was called RCNN. And so for object detection. But if we did RCNN, it would have taken us about 31 GPU years to do this. So it was absolutely infeasible for us to use RCNN at that point. Right now, there's stuff called like mask RCNN, faster RCNN, so it's much, much, much faster. But back then, it wasn't, and our intent was not to create a novel object detection algorithm. So what we wanted to do is we wanted to try something off the shelf, and if it didn't work, then we would start like investigating something novel, right? So we used a previous state-of-the-art object detection model called DPM, deformable part models. And we were able to detect all the cars in 50 million images with 200, we had a 200 CPU cluster. And we did this in 2 weeks. So now what do I mean by detect cars? So we split the task into 2 tasks. The first thing we did was we had a task that told us whether or not there is where there are cars in the image. So it gives us a bounding box where there is a car. Once we get the bounding box where there is a car, we add it. We put it through a CNN, the like simplest CNN you can imagine, a convolutional neural network, what we call AlexNet, and then that is trained to classify the car into one out of 2657 classes of cars. And so you can imagine this is like this is the convolutional neural network structure that won the first ImageNet challenge. So basically in 2012, the ImageNet challenge had been going on since 2009, and in 2012, for the first time, this convolutional neural network, by far, sorry, it got first place, and it really blew everything out of the water. Like the error rate was so much lower than the next best thing, and this is really what brought back deep learning into the mainstream. So after we did this, we detected about 22 million cars, and this was about 8% of the automobiles in the US. And you can see, you can ask how well are we doing? Well, so at the very fine grain level, like let's say at the model accuracy, so if we want to say this is a Honda Accord, 2005 Honda Accord, we get about 52% accuracy. And at the very, very, very fine grain level, this means this is a 2005 Honda Accord LX, so the trim, the body type, the year, etc. We get 31% accuracy. And you might think that this is not great. 31% doesn't sound great. But for fine grain image recognition, which is a very difficult task, and for 26-way classification, for us, we thought we did pretty well, especially with like off-the-shelf type algorithms where we did a whole bunch of stuff that I'm not going to talk about for efficiency reasons. So we were shaving off accuracy. We were saying, okay, we'll take a hit, 1%, 2% hit in accuracy because of efficiency. And then as you get less and less fine grained, like for example, which country was this car manufactured in? You get better and better accuracy. So for example, the country that the car was manufactured in is like 84%. And excuse me, the point I want to make is that the types of mistakes you make matter for our task, right? So if we're routinely mistaking expensive cars to cheap cars, or like confusing expensive cars to cheap cars, then that's going to mess up our demographic analysis. So here I'm showing an example just to make the argument that our mistakes are kind of reasonable. So here we our biggest mistake is like we confuse crew cabs with regular cabs, or extended cabs with regular cabs. These are all types of trucks. So, I would say it's kind of reasonable. Or like coupes with hatchbacks or convertibles. And so in different poses, when you're looking at a car in different angles, it's very conceivable that you can't tell the difference between, a coupe and a convertible, or a coupe and a hatchback. So now we've detected and classified all the cars that we have in 50 million images in 200 American cities. Now, what's left to do is to use this information to study a whole bunch of things. So the first question, the very simple question we ask is, can we tell how green each state is? Can we have any indication of this using the metadata that we have for the car? So for each car, we have a lot of metadata. We know the efficiency of the car. We know the price of the car. And we have a whole bunch of other metadata. So what we did was we aggregated using our data, we aggregated we represented each state as by a number, and this number is the expected miles per gallon of the cars in that state according to our data of the cars in that city. And then we compared that to data from the environmental from the EPA, from the Environmental Protection Agency. So here on the left, you see the per capita of carbon footprint. This is ground truth as shown by the by the EPA. And then on the right, you see the average miles per gallon as predicted by us. So, so when we look at just the correlation, it's pretty, it's about 0.7 something correlation. But then, so we get the coast right, but then, we make some mistakes here, right? Like, so Nevada, we get it wrong. And my assessment is that the cities that we have in Nevada are probably not representative of the entire state. But what's really interesting is that we saw, according to our data, that the city with the highest, the greenest city was Burlington, Vermont. And we read up and then we found out that Burlington, Vermont was actually the first city in the US to have 100% of their power come from renewable sources. So it was great to see that our data, saw that the greenest city was Burlington, Vermont, and that was actually accurate. And the least green city, according to our data, is Casper, Wyoming. And Casper, Wyoming is actually the least green. Wyoming is the least green state in the U.S. according to EPA data, and it's a coal state. So Casper, Wyoming, I believe, I don't remember the exact number, but it's overwhelmingly a coal economy. Okay, so the second question we asked is, can we say anything about income segregation in cities? So if we just looked at, so don't look at this math, but if we just looked at the price of the car, at the average price of the car at each GPS point, and we looked at this thing called Morin's I statistic. It's a measure of spatial autocorrelation. And higher just means more segregated. And so could we say anything about income segregation? So we plotted a subset of the cities we have by income segregation, and we could see that the most segregated city, according to us, was Chicago, and the least one was Jacksonville. So when we look at Chicago, we can further visualize it. We can see that red represents statistically significant clusters of expensive cars. And yellow represents statistically significant clusters of cheap cars, and the creamish color represents just like no statistically significant clustering by price. So we can see that there is segregation here, and if you look at the census data, you'll see that the red is basically in the wealthy neighborhoods. But then we saw that there isn't as much clustering by car price in Jacksonville, at least according to our data. Okay, so far, all we've done is we've used one particular attribute of cars to predict one particular demographic attribute. So now the question is, can we use all of the data, all of the things that we know about the cars that we've detected in a particular neighborhood, and use that to train a model to predict demographics? So what we did is we aggregated 88 car attributes. So for each zip code, or when we do voting for a precinct, we represent it as a vector, and each entry in the vector represents some feature of a car. So the number of cars per image, for example, is kind of a proxy for the density of cars in the neighborhood. The average car price, the percentage of, let's say, each make, like the percentage of Hondas, Toyotas, etc., the percentage of whether the car was made in the US or not, etc., etc. So then we just did simple regression. So regression with L2 regularization to train a model to go from these 88 car attributes to various things, such as income. So we used all the cities in that you see as purple, in purple as training data. Excuse me. And then all the cities in green as test data. So how did we do? So here are some actual versus predicted values for median household income. So from now on, I'm just going to show you like results like this. And so you can see some maps in Tampa, Florida. So here's the least wealthy zip code. So we have actual versus predicted maps. And then you can do fun things like, what are the car attributes that are most highly correlated with expensive neighborhood, wealthy neighborhoods versus not so well-to-do neighborhoods. So turns out the percentage of foreign cars is very highly correlated with wealthy neighborhoods. But for example, old cars are, not very highly correlated with wealthy neighborhoods. The average car price is very highly correlated with wealthy neighborhoods, which makes sense. Then we do the same thing for voting patterns. So here is actual versus predicted values. And here is a map where red is a Republican city and blue is Democrat. And, actual versus predicted values. And then here I show you a different kind of map. It's actual values of voting patterns. And then on the right, I'm showing the ratio of extended cab trucks to, sedans to extended cab trucks, which in our data set ends up being a pretty good predictor of Republican and Democratic precincts. And so here I'm showing you a much more high resolution kind of maps of actual versus predicted cities. And you can do the same thing here. You can say what are car features that are most highly correlated with Democrats versus Republicans. So it turns out the percentage of sedans are very highly correlated with Democratic precincts. A high density of cars, which is the number of cars per image. And then all trucks seem to be very highly correlated with Republican precincts. And I have to say that our data set is very skewed towards Democrats in general. And also it is cities, so cities also tend to be Democrats. So I think what we're picking up here is probably that more cities tend to be Democratic because, it makes sense that cities have a high density of cars per image and maybe a lot of people drive sedans when the cities, but, we don't know exactly why we have these correlations. And then we can ask questions like, given that I'm in an area where the ratio of sedans to trucks is high, is more than 1, what is the posterior probability that the people there voted Democrat? And then I can ask the same thing for a Republican, and it turns out to be pretty high. Okay, so we can ask the same question. We do the same thing for race. Here are some example results. And then you can do the same thing, like what are car attributes that are most highly correlated with various, different races, right? And then you can decide for yourself if you believe in this. Actually, most of these we had to verify, and we had to do some extra reading and research for market research to make sure that they made sense. Finally, we do crime rates, and this is the kind of stuff that actually made me want to work on things like bias and data set bias, because if you're doing data mining and you're trying to predict crime, you only have data about whose crime was reported and whose crime was caught, and that gives you all sorts of data set bias. But anyways, so here we have actual versus predicted values, and then again, we do the same thing of what car attributes are most highly correlated with crime. And what was really surprising to me, well, the number of cars per image makes sense because if you have a higher density of a population density makes sense, you'll have more crime, numbers wise. But then we saw also vans. Then that was weird that the percentage of vans was highly correlated with crimes. Finally, something I'm really interested in is doing this analysis over time. So Google's has this tool called time lapse. So you see here New York City, Brooklyn in 2007 versus 2014, and you can see how much it's changed. And then you can see Detroit and how much it's changed in the opposite direction. And the question is, can we do this analysis at scale using computer vision? And so there we have some very preliminary results here. So here I can show you, this is the change in the percentage of high school educated people. So red means it's decreased in New York. This is New York, and blue means it's increased. So here is actual, here is predicted, and this is not quite there. I mean, but I'm really interested in doing this kind of work. So yeah, one thing I'm really interested in is that right now I'm talking to a lot of sociologists, and I learned that there are things that things that people are doing to undercount certain populations in certain places, so that they can have a different population measure for redistricting, and there's all this political stuff and gerrymandering. And I think it would be so cool if you had a separate entity that's not affiliated with the government that tries to predict census data using a lot of different publicly available images. So, I mean, I wanted, I'm interested in seeing like what that would look like. Basically, I mean, this talk is just supposed to, I just wanted to show that we can use images to understand society. We don't want to make too many claims about like our accuracy or whatever. That's a danger in our field right now, like over claiming things. But I think that we could do some interesting things, and I hope to see more of these kinds of work. And yeah, let me know if you have any questions. Gonna
Thank
go
you,
back to my
Tim.
chat. Sorry?
No, thank you. We can still see your screen. And we normally have questions typed in. And I think one of my questions was when, because the thing with us with our practice right now is that we have so many people who are already just out, running this code. And one of the things that surprised me was when I started doing deep learning was with 3 lines of code, I could have results that I honestly did not know what the models did and what actually those meant clinically. And so I wonder if you have some advice for people who are getting started to just understand. They don't, people probably will not have commitments to do a PhD, but just what would you advise for people to do so that they can be able to understand the lingo and be able to sift through the hype and the reality?
Yeah, so I think that there's 2 things. I'm actually writing a paper about this. Like, there are 2 things that are happening right now at the same time. One is the move towards democratization of AI, right? Have open source tools like TensorFlow, have pre-trained models, have data sets, etc., etc. And then the other one is like we've seen that there's issues with bias, and AI is being used in really high stakes things, and clinical stuff, that's a high stakes, based kind of thing, right? You're dealing with people's lives. And the thing that's missing for me is that these companies, when they're putting out their software to be used by anybody, or when they're putting out their models or anything, they're really not giving us enough information, right? It's, we don't have enough, we don't have enough guidelines for, overfitting. For example, you should train on a certain data, you should test it on a particular data. Obviously, your train and test set should not overlap. And another thing is that the distribution of your training images and test images, often if it's different, like let's say I have, training images where I like took a picture with my phone, with my iPhone, all pictures with my iPhone, and but then like my test images are like coming from a completely different source. I probably, if I train like a network on one type of image from my phone, it's probably not going to work on the other type of image, right? So it's just like these things, or like like another thing is hyperparameter tuning. Maybe you'll tune your hyperparameters over and over again to get like 1-2%, because there's so many papers that said we did this and we got 1% better accuracy, 2% better accuracy. But in real life, it's unclear what that means, because it's unclear. Your test set is probably going to be changing over time, right? So I don't know, like, if I have great answers. My answers are like, you don't always have to know exactly. Well, depending on your setting, you might not always have to know exactly what your model is doing. But I think like understanding the metrics, like not just looking at a single accuracy metric on some data set. You might want to know, your particular data set, you might want to break it up into certain groups, different kinds of groups, for example. And that comes to my bias paper that you just mentioned. Is like, I'll give you one specific example. We audited these commercial gender classification systems where they look at a picture of someone's face and they say, they give you a binary label, male or female. And then, on our data set, IBM or whatever gets like 97% accuracy. That might sound great. But then you break it up. You say, okay, how does it do on women, female versus male? How does it do on darker skinned female versus lighter skinned male? And then you find out that like the error rates on darker skinned females are like 33%. And then the error rates on lighter males are like 0%. You know, now you're starting to see like that this is a very, you know, I don't know if you wouldn't want to use this data set, this API in a very high stakes scenario. And then, you know, you want to look at the false positive rates, the false negative rates. So I think like understanding maybe like that, you know, just because you train something off the shelf and you have some accuracy that sounds high, that's not the end of the story, right? And so this weekend, actually, there is a conference called FATSTAR, Fairness, Accountability, Transparency in Socio-Technical Systems. And I encourage everybody to sort of actually look through the maybe proceedings. I'm going to type it in chat maybe, just so people know which conference I'm talking about. It's happening this weekend. It's actually going to be streamed, and it's an interdisciplinary conference. So for example, if you're in healthcare and you want to know what all these different accuracy metrics mean, there are like translational tutorials to you know, have across disciplines, right? Maybe a tutorial by a machine learning person that is meant for someone in healthcare, and vice versa. Like if you're in machine learning and you want to understand certain things about healthcare or law, whatever, there are tutorials like that. So I encourage people to kind of look at this conference and just try to kind of investigate more than just have a single accuracy metric and call it a day.
Awesome. I think Sunil asked, did you use the data label from Craigslist and cars.com at all?
Yes, I did. So what we did was so that's because I was talking about how it doesn't work right here. Oops, sorry. So yes, what we did was we did use the data from Craigslist.com and cars.com a lot. Yes, we did. And so and then we also used the data from Google Street View. But in a subsequent paper, I do something like I have a fancier model with domain adaptation to try to maximize the accuracy on Google Street View images while also using the Craigslist.com and cars.com. But in this case, we just did something simple, like we tried to transform the images from Craigslist.com and cars.com to look more like Google Street View images. So we had a filter that blurred them a little bit and things like this. We applied some transformations. And then we actually we replicated the Street View data because we have about 33,000 or so Google Street View labels, bounding boxes, but like 300,000 of the Craigslist and cars.com cars. So what we did was we like replicated the Google Street View images too. So we have like a more balanced training set. So we did some rudimentary stuff like that, and that, you know, increased, that had a huge impact on our performance as well.
I have another question on privacy when it comes to models. And I know this is not directly related, but, you know, since we don't have many PhDs in our community who have AI stuff. And so I read recently about something called model leakage. So even if you train some data, you can train some models using sort of de-identified data, and because that's the big thing about healthcare data training. But but still, that in some cases you still can learn more about what data set was used to train the model. Could you maybe clarify that to us who may not?
Yes. So I think that this is a huge thing. I mean, I think right now, that's why, like, for me, that's why this field of fairness has grown, and also privacy. I mean, it's related. And I think it's going to continue to grow exponentially because, so I think one thing that people are doing is trying to do everything in a non-centralized way. So instead of like, let's say you have a phone or something and you want to train a model, instead of having your data sent to some centralized server and training a model there, and then returning your the results to your phone. Do something like on the device. Do as much of this work as possible on the phone itself. So have distributed models and training on the phone itself, so that people don't have to send their data to some server to be like for a model to be trained or something like this, you know? And so like there's people are trying to do this kind of stuff, and there's other things people are working on, like differential privacy is another one. What's really interesting is that there is a huge overlap between people who work in fairness and people who work in privacy. So Cynthia Dork is another one. She basically she invented differential privacy, but she also works a lot on fairness. So this issue is something, yeah, like it's something that's gonna start to be, I think, bigger and bigger. And I can see why you were very interested in it, because in medicine, I guess that's like all. I'm just about to start working on bias, looking at bias in medical data. And I just realized like how much more of a hoop you have to go through to de-anonymize the training, like the data, and you know how many more checks and balances you have to go through before you actually start using it, which is obviously a good thing. But yeah, I think this is going to start being like something pretty big.
So we have one good long last question from Justin. One of the bridges we're trying to traverse on the medical imaging AI side is the prescriptive model, not necessarily predicting the current state, but seeing likelihoods and prognostic features to improve a patient's outcome. You talked a little bit about this with Google Time-Lapse. Are you suggesting this kind of prescriptive model? And how hard is the leap from a present state prediction to a sound predictive prescriptive?
Yeah, I think it's hard because, again, like, you know, I think it's hard because, especially if you don't have enough historical data and you don't know, like, for example, I'll just go with the cars, right? The association between people and cars could even change over time, right? Like, so maybe that's not how it is in medicine. Maybe like a particular feature about a person, something about a patient, if you know the patient smokes, maybe it'll always tell you something else about the type of disease the patient might have or is likely to have or something. So maybe that relationship might not change over time, which might make it easier. But in my case, you know, sure, like a Prius is highly associated with being an environmentalist in 2010, but that might change in 2020. Maybe in 2020, having that car, you know, so you have to have some sort of baseline to retrain your model every so often to also get that baseline, you know, car people relationship. What I think honestly is that I think that in the machine learning community right now, or like in the deep learning community, I think we need to work more on causality. And I've been trying to like learn more about causality, like models and causality. You know, like a lot of people were, I guess, in health, you know, a lot of people who are interested in machine learning and health use this, like probabilistic graphical models and causality and stuff like that. And I'm trying to learn more about it because I think that we have to try to bring that more into our framework, to try to do something like predictive and not just like correlations, you know.
Okay, that makes sense. Okay, and Brian, can you say a bit about how you selected the gold standard that was used to train your model? Just found experts. Brian, your question. Okay, so can you explain how you selected the gold standard that was used to training your model? I think he wants to understand. And Brian, you can always retype your question if I'm saying it wrong. How do did you just find experts? Like how?
Yeah. When I did this, when we first tried, okay, so when we had two sources of data, right? For the data from Craigslist or like cars.com, we didn't need to have experts because I searched for 2005 Toyota Prius, and with very high likelihood, I'll get an image for 2007 Toyota Prius, right? So when I scrape Craigslist, I already have a labeled, an image labeled with the type of car it contains. I have to do some cleaning up, like, you know, some NLP, but I didn't need experts for that. But when we get to Google Street View images, like this part, yes, there we needed to hire experts. So here is what we did. This was a very painful kind of thing. We first went to Otis. So the good thing is for each car, we have example images. So if you, once I give you a bunch of cars and you annotate them, I can personally check whether your annotations were correct because I have example images for that type of car. So once you do it, I can compare it with my example images and see if you did the right thing or not. But before that, first we had one expert. So we found one car expert, a freelancer. Somehow we advertised and we found this guy. Once we found this guy, we had him annotate a bunch of our images. And once he annotated a bunch of our images, we used those as a gold standard to test other experts. So we massively advertised trying to find experts, and we wanted to, well, you know, we had a limited amount of money, so they had to be fast. And so they had to annotate like one image per minute. So like, I think in an hour they had to do 60 at least. And they had to do it accurately. So we had somehow, I don't remember what accuracy we came up with, but they had to have a certain amount of accuracy. And so the way we tested their accuracy, the way we tested them before we hired them was using the first set of images that were annotated by the first expert after we checked that they were accurate. And so we had about 100 or more experts, I don't even know, for a whole bunch of time. And we had them annotate these images until we ran out of money. And then we regularly checked whether or not their annotations were correct.
Okay. Well, I don't think we have any more questions. And so, yep. Okay, so some thank you coming in from our chat list. So thank you so much for your time today, Timnit, and thanks everyone for attending. We always need your feedback, and we can continue the conversation. Our chat, hashtag is RADAIJC, Rad AI Journal Club, and so we always continue some of the conversations post attendance there. And so, like I said, the next one we're trying to do around a theme of FDA approvals, and so we hope to see you next month. Thank you so much.
Thank you.